Um, so any questions about this material? So one-to-one and onto, just that for the time being. Things that you've seen before, but so we are taking it to a different level. We're doing, let's face it, we're doing pre-calculus.
Really?
Yes.
Wow.
Just, like I said, it's just on a different level. So the functions, things like functions, one-to-one onto, domains, and things that just about to come, they all technically considered before calculus, and then so that you know when you start calculus, you know what to do with them. Okay, so there are no derivatives. Not gonna be derivatives, or really nothing about differentiation or integration. We're doing very basic things with functions, and that's what pre-calculus initially is about. But pre-calculus concentrates on things that are meant for not just calculus. Unfortunately, often, most of the time, concentrates almost entirely on material needed for calculus 1. And so that's why functions in pre-calculus are all one variable, from numbers to numbers. So what we're talking about from x to y, in pre-calculus, it's x is real numbers, y is real numbers, or some kind of subsets. Okay, and so then you arrive to calculus 3, and then you have to actually make that leap into functions that are not necessarily numerical. Okay, so so in that sense, we are relying on your more recent experience with calculus 3, because that's what provides you really with a multitude of examples of when these things becomes less elementary, and they really say a lot about functions. As an example is what just a parametric curve that we saw just yesterday. There's a parametric curve right in the middle, and then just that one little picture illustrates perfectly two things, not just one thing of what we have talked about, but two. So that red dot, once again, demonstrates that the function is not one-to-one. Okay, and then let me plot green dot over here, which proves what?
It's not on the curve, is it?
Which proves, what does it tell you in this our new language or old language about the function?
It's not onto.
It's not onto, right. So something that that's not the right way to put it. That's something that you do not have such a perfect example in calculus 1. So this is entirely a calculus 3 example, and it really perfectly illustrates of these two concepts right away in 1 plus. So not one-to-one intersects itself, and at the same time it's not onto because there are missing points. And we have even more, that is more recent picture right there. It's pretty much almost the same thing, but the difference between the image and the graph, right, is visible here. So so once again, a parametric curve, you see the image, which is that circle over there, which lies within our space of outputs. That xy plane is where you see your curve, but really that's only the image. So once again, this is the image. In the meantime, it is the graph is that it lies in the three-dimensional space. Okay, so and then from the graph you cannot really see, for example, whether it is one-to-one or onto. It is the examining image appropriately will reveal that. So all that good, and that's when if you feel overwhelmed with abstraction, which is unavoidable in mathematics. So and sometimes it's hard to think what you to do with those concepts. Go through examples, as many as necessary. That's a example, a good example, and to test your understanding of these two concepts. But then it's certainly not enough. And the functions that are the functions that you see in the calculus 3 are just as good tests of your understanding. So functions of several variables, for example. So it's kind of on the different end of the spectrum parametric curves and functions of several variables, and they are surfaces. I had that illustrated here somewhere. Surfaces like this one in the middle. Situation changes dramatically because, as you can see, the main and codomain have been flipped, sort of. So it was for parametric curves, the right here, the domain is one-dimensional, t, and the codomain, the value where values apply, is two-dimensional, right? Flip it around entirely, and what we see here is the domain is, unfortunately, the color is not preserved. Let me just make a new picture just as well. So if I'm plotting a parametric curve, okay, so I'll put this is my t to emphasize, you know, where parametric curves come from, and this is my domain. Okay, and the graph might look like this, as I suggested previously. Okay, with this being, I'm sorry, I messed it up. I was going the other way. Okay, let me start over. Okay, so the domain is this domain. The domain is only t's, the input, and for each of those there is a point. Okay, the point, where does that point lie? It lies among the outputs, so that's where it is. So this is codomain. Okay, and then you have the same three-dimensional space, and but things change. So I'm talking about functions of two variables. Same three-dimensional space, but this time this is my domain, and this is my codomain, the values. Okay, and once again, then the idea is that I try to express here. Every t over here gives me a value here somewhere on among the in the codomain. So that's the value. That is say f of t. Okay, and here, however, we have way more values for the domain. Okay, and so but the plan works out the same way. I have to find f of x here somewhere. So if this is x capital, okay, so variable 1, vector variable x capital, its value of function under that the value of this function of x has to lie on the z-axis. Okay, and so that's the way I arrange things. So this one is z is equal to f of x. And here I'm talking about x equal f of t. Okay, so once again, in either case, x is the vector. Okay, so I'm sorry I didn't put a vector here. I didn't capitalize it to make that point. So it's a vector. In fact, vector in it's xy. Similarly here, this one is a vector, and it is xy. Just two-dimensional vector, so it's xy. Okay, so that's the similarity. The graph is then different because of the difference in especially in the domain. The domain is so much bigger in the latter case, so the graph is much bigger. It's not a curve anymore. It is a surface. Okay, so and then once again, we just had an example of how you examine with parametric curves. Examining the image is very productive. So instead of looking at the graph, which is this graph, and that's the graph too. So it's very productive to look instead at the image. So say I'm looking at the image. So in other words, I'm throwing out axis t, and I'm left with just x and y. Okay, and then my curve becomes, well, maybe that doesn't matter what it becomes exactly. It might be like this, and then you can examine, for example, as we just discussed, you can examine whether you come back, and that demonstrate that it's not one-to-one. You can also notice that there are points not covered by your image, and then you know it's not onto. Not so easy with functions of several variables. It's actually you never really go and look for the image, because look at where the image is located. The image of the function of two variables lies where? Where? The image? No. The image of two image. It lies in the codomain. It's all possible. It's in other words, is the range that you might remember from calculus 1. Determines the range is all values of the function. So as you can see that that graph over there only tells you the whole story more than you might need. But if you look at what that graph traces among the codomain, it gives you this curve. See, x and y, those same x and y as you have over there. However, it's a different story now with the function of two variables. The domain is so large and the codomain is so small, so then there is really nothing to see here interesting happening. The information is very limited in order for you to understand whether or not you have one-to-one and onto. The curve, you can sort of almost know where you were, even though you don't know the exact value of t. At least you know that you revisited a point. You know that you did not visit another point. You visit all of these points you have visited once, and this point you visited twice, and this point you never visited. Okay, so that's very revealing. It's like you have a map, and that's what the image of your trip. So once again, that analog I want you to think about is that the original function is a road trip. Your trip plan, when you plan when and where you're going to be. If you combine together, you have a graph. So you have time and location at the same time. Time, t-axis, location, xy plane. That's your map. If you throw out your timetable, t-axis, you end up with the image. Okay? And that is your road trip, which might end up, you might actually mark. That is frequently done with parametric curves. You can mark points with some information about when. Okay, so I could say this is t is equal to 3. Okay, so that information that you lost by removing the t-axis, it can be at least partially recovered in that manner. If you mark the point on your image on the curve to figure that out, which is probably a good idea of how I would imagine a road trip. If you want to have the full look of the road trip of your plan, then you have your path and you mark your stops. You stopped here at this time, that time, or day and time, how much time I spent everywhere. So that's your plan of your road trip. So that's a good way to represent it. But without those markings, all you have is the image. Okay, but think about, once again, road trip is a function from time, which is what you have, to location, which is where you're going to end up. And also, you can figure out that you certainly can revisit the same location twice. That's no problem. Also, there will be obviously locations that you're not going to visit. So it's not one-to-one and onto typically. With functions, so that's the metaphor for functions for parametric curves, road trip. Okay. What's the metaphor for functions of two variables is a terrain. A terrain which gives you so your plane, xy plane, is still your map. But what is the value of z is the elevation. So then your graph is almost literally the terrain that you might be seeing. Not seeing, so there is no driving anymore, but that's what you face. That's frequently the way you're going to need if you are going for, I don't know, hiking, that you need that kind of map. That gives you not only the coordinates and maybe cities or trails or rivers, it also gives you the elevation so that you know how much you got to climb. That's how you end up with a function of two variables, and that is the it is a function. The input is your location given by two numbers, which is your place on the map, and then there is an elevation. Okay, so you may have seen, well, or maybe you can tell me what. How do I make a two-dimensional map this way? You may have seen these. So, what does an elevation map look like on a piece of paper? Yeah, yeah. Rings, right. So what do those rings stand for, or what do they supposed to?
Contour lines.
Contour lines, right, like this. Contour lines, and those are fixed elevation. So they are usually marked like 200, 300, 400. Okay, so these are the elevations, and then if you follow that path, you'll stay on the same elevation. Okay, so these are just the two shortcuts that people take in order to do what? To handle a three-dimensional situation with only piece of paper which is two-dimensional. Okay, so but other than that, what's behind it is still function with three variables involved, and they produce, and then the graphs they lie in the three-dimensional space because three variables. Either you have two inputs, one output on the right, or you have one input, two outputs on the left. Either way, you have to have three variables to handle, and that's where the graph lies. Okay, so if you think about it now, let's examine what's so clear, I hope, about one-to-one onto issues with the parametric curves on the left, but in the for functions of two variables. So how can you tell whether it is one-to-one? Let's start with one-to-one. How can you tell from either the graph or that picture, the contour portrait, or one of those contour map maybe that you see here of that same function? How can you tell whether it is one-to-one?
If it doesn't overlap.
Well, there is not overlap where?
On one of the axes.
We did a different thing. So notice how similar we acted, how differently we acted with these two. With parametric curves to move down. Well, not we did it. That people do it. We hid the input variable t, time, one axis to remove in order to end up with two dimensions. In the second one, the axis that we hid was z, the output variable. Okay, so we're looking at now at a problem that is stated in exactly the same definition, but the answer would be very different. So what does it mean for the function to be or not to be one-to-one? That's the definition. Okay, so same value. Let me write it. So z. Let's just say it this way: f of x is equal to f of x prime. So that if there are two different x prime, then it's not one-to-one. So this is not one-to-one. Is it one-to-one? So I just wrote that equation from the definition in order to compare to what we're looking at here. So the function that I plotted here with those contours, is it one-to-one or not? No.
No.
Why not?
Because it just doesn't look like it.
Well, look at the definition that's written over there. This is z. This is z. It is the elevation. So x and x prime are two locations on the map, the inputs. Are they or do they not have the same, could they have the same elevation? Two different locations, could they have the same elevation? Look at the map, at the picture. Do they?
Yes.
Okay.
So, like, are you looking from one circle to the other circle?
No. One circle. One circle had a bunch of points. So this is x, and this is x prime. They actually produce the same elevation, right? So whenever you have a contour, right away it's not one-to-one. So you can actually walk along it and stay on the same level.
I have a question then.
Yeah.
Why are there three different rings? Like, I'm kind of confused on what type
Well,
of
they correspond to the different values. So the what I blew, these are
okay,
Z's.
you said those were like the elevation maps.
Yeah.
Oh, okay, yeah, okay, gotcha. So-
You can take
Yeah.
those rings and sort of
Yeah.
lift them
Gotcha.
and create a
Yeah,
Okay.
got you now.
right. So okay, so the answer is no. And not only no, it is typically no. It is actually hard to think of a function of two variables that would be one-to-one.
Yeah.
Right, so I'm trying to think of it, I cannot really. So there is only one, each point has a different elevation. Probably not. No, nothing, you certainly cannot see anything in real life. And if you think about terrain, there will be always a couple of locations next to each other with the same elevation. Don't forget, however, the only point that is getting closer to that is a peak. A peak has only one location for that elevation, right?
Unless the peak is flat.
Right, unless it's not a peak of plateau, or there is another peak of exactly the same height elsewhere.
Yeah.
Now, second question, what about, so the answer is no, not one-to-one. What about onto? What? Is it onto?
I'd rather not answer.
Yeah, I'm gonna say yes.
So back to the definition. So always, when in doubt, this is the definition. Onto, for every output, there is an input.
Yes, because every place that there's on a map, there's an elevation.
No, backwards. For every elevation, there is a point on the map. From the output to input, moving backwards. Just like that green dot over there, it does not have a counterpart among, you will never visit there. There is no time when you were there at the green point. So similarly here, do we have, for every elevation, do we have a location with that elevation? The answer is
Yes.
no.
What?
Because like it goes
Typically.
from 200 to 400, you could have an elevation of 500 and there's no place on the map.
That's right.
But I thought we're looking at this.
We're looking at this, exactly. See,
Then you could say
that dot,
like any line ever. Like you just pick a point that's not on the line and just be like it's not on to because it's not on that.
no, but the metaphor is an elevation, a terrain. So, well, metaphor, well, you object to the word metaphor?
No, like I don't understand this at all. Like, we need a different scenario.
Well, because, no, metaphor, it is like a manifestation of a big idea in some particular situations.
Right.
So the big mathematical abstract idea has these manifestations, instances, if you like.
Okay, I understand, but like I just don't get where you can pull like I know that 500's not on there because 500's not on there, but I thought we're looking at from 200 to 400. So that for every output on that.
Well, but you can see that if the highest peak is 500, then there is no 600. That doesn't matter what that is. If the highest peak is 500, which is what I just make it clearer, then there is no 600.
But I know that. But you said for every output there's an input, right, or whatever.
That's right. So for the
on that graph,
where is the input for 600?
But it's not on that graph. So what are we
Exactly,
looking for?
exactly. So the answer is no.
I think the answer is yes, because there's a scale on that map,
Yeah,
and it's evenly graded between those two lines.
Yeah.
It's
Right.
assumed to be evenly graded, so then you have a distance and the slope, so then you can find the elevation on any point between those two lines.
No, the way that this is what the contour map usually looks like. So contours for different elevations at say 100 feet at a time are drawn, and then there's a dot usually indicating the highest point, also supplied with an extra number, and then you know that there is nothing beyond it, right?
Then I have a question. So when can you make an elevation map onto?
If it is a small map, for example, and you're standing on the slope, which only goes beyond the map. So imagine like this, a plane.
Yeah.
So and then you pick a part of it.
Okay.
Then it is onto.
But we picked a part right here. I mean, I don't get that's not.
No, there's based on this picture, there is nothing beyond 500, right? There is no highest point beyond 500.
Yes.
So then there is
Why are we worried about 600 then?
we're not, just for the sake of the definition, is it onto or not?
Yes, it's on to.
Only if you limit your codomain to 500.
We did. It's 500.
No, I don't think it is fair to say it this way. I mean, even though it is, if you are the one studying it, it is up to you to choose the mathematical setting that you prefer. So you could choose the codomain to be up to 500. It's entirely your choice, and then you would be correct. It is onto.
But you told me the peak is 500, so
Right.
why don't we limit it to 500 if that's the peak?
Eliminate? I don't want to.
No, limit
Li-
to 500. Why
Well,
would-
no, that's a question for you. Why would we?
Why would
We usually, if we exploring a surface of the Earth, the actual altitude might go to 10,000 feet, right, easily. So why would we ahead of time limit our codomain, our possible values of elevation, to any particular number that depends on our particular choice of piece of the Earth? I would not limit it at all, because we don't know how far we're going to go. So that is not a non-mathematical question, frankly. But
I was just saying, we're looking at a graph that goes to 500.
Right.
So why do we need to worry about 600? Because it
no,
only goes to 500.
well,
so
that
it's
if
not-
you don't worry, it's totally your choice to choose. Well, let me follow that to show that what we could do. Choose y, the codomain, to be, say, to be specific, how about 200, 500?
So now it's on to?
Yes.
Thank you.
Well, just to demonstrate that you really have this much flexibility. You are choosing your domain and codomain. And so if you choose a codomain to go up to the maximum of the value, you'll have probably onto. If you are talking about some unpredictable situation, then you might choose the codomain to be all real numbers, and then certainly it won't be onto. But it could be. So that is the complexity. Even though we took only the two simplest things in calculus 3. What else did you see in calculus 3 besides these two?
I'm still in Cal 3. So
Okay.
I'm not-
Now what? And just I just wonder if anybody remembers
Like types of graphs?
type of functions. Yeah. Vector fields, unfortunately. Vector fields. So just I'm not going to go into that. I think these two pretty good examples capture a lot that you can think of. But those are these. So this one is from R to R2, parametric curves, functions of two variables from R2 to R. And then you can imagine that the complexity is not going to go down if you go both of the inputs and outputs are two-dimensional. So things become nasty, obviously. But this is fine. So this is a good start. Like I said, Calculus 3 is a very good place for drawing examples. We're not going to do anything else from Calculus 3. We're not going to do differentiation or gradients or even vector fields. Nothing. Just functions that you encounter in Calculus 3. We use them as examples to illustrate ideas that actually come way back from pre-calculus, one-to-one and onto. Okay. So, and you can see that typically it's not the case to have one-to-one or onto. Okay, so one question, so let's set vector field aside. Here's a question for you. How can these two functions interact? These two. These two. These two exactly, two functions. How do they interact? I'm intentionally using the word that it does could mean a lot of things, so that just to see if you remember what this exactly I'm talking about.
You can see your elevation change over time.
That's right. That's right. That's right. If you are you have your trip on the map XY plane as a function of time, but then you realize that there is also elevation, and then you might be interested in how hard you got to be climbing. So you have to combine these two together in order to know how your elevation is a function of time. And the word is how do I combine these two functions together? To find elevation as a function of time.
Saying like take the function, put it in the function.
Yeah, there's a word for it.
Yeah.
Yes, composition.
Yeah.
We are doing composition, so that's what we're driving at to show you. So the first function is time to location. That's the first function, parametric curve. The second one is location, elevation, right? And now you want to do this. How? Well, you realize that this location is the same as that location, okay? And that's called a composition. So if I call, how about I'll call this G, just so that there would be no confusion. I'll erase this. G. Okay, so then it will be, I am substituting, indeed, F into G. So it is F followed by G, which unfortunately in algebra are written in the wrong order. So you first write G and then F. G, circle, F, what I'm talking about. So once again, this is F, this is G. And if you did make a two-step all the way through, it gives me time, elevation as a function of time. Composition can also have a very specific, you can actually show what it is. It is a trip on the XY plane that we have built. It is sort of lifted to my terrain. And so I am really traveling not on the map, which is flat, but on the elevation, on the terrain that has some various elevations. So that's the curve. This is what this one is, G composition F. So as you can see, we're not doing addition, subtraction, multiplication, or division. So although those calculus concerns we're not concerned with that. Compositions work always. So in set theory, in this abstract view of everything, we don't have numbers, we don't have vectors, we don't have anything, and so we cannot, for example, add two functions together because there are no numbers. They are not numbers. But we still can do compositions. So as you can see, two very different functions are composed. Yes?
How can you tell time on that? To me, it just looks like X, Y.
You mean the last picture?
Yeah.
Well, you can't. I mean, the picture is incomplete, right? So what I'm trying to say here that this is F and this is G. Okay, so you start with your time here, and then under F it creates a curve on the XY plane. That curve is lifted to the surface, and then the surface, you will know the elevation if it is on the surface. The only question is when, right? But that is where that markings that we have over there come into play. So for example, if this is t is equal to 1, that this is also t is equal to 1. Okay, and if this is at the end, you have t equal to 3, then you will know when you are on the, how high you are, right? I mean, think about it, how it works out, that composition. What is the meaning? I didn't actually write out, but G composition F of T is G of F of T. So the information is all there. So you plug in T, evaluate F location, then that location is plugged into G, and you have your elevation. So it's exactly that. So that is just an illustration. So it has actually more information than you need. Where on the surface you are located, but that's really not what we care about. We only care about the elevation. So see, that's the function from time to elevation, which is actually, by the way, with all this complexity, the end result, this composition, is a numerical function. Time is a number, elevation is a number. So it's just a graph. Okay. So you can certainly pick a particular parametric curve for your function f for your trip, and then for elevation pick some function of two variables. You plug them in and you have it. It's really no trouble. But I don't want to stray too far away from abstraction that we are facing. And the composition, we have to look at them in the abstract rather than in this specific example. I don't want it to be too specific here. So so let's define it. So then we have two functions, f from x to y, g from y to z. Two functions. Okay, then. So, so as you can see, the only thing that they have in common is that the codomain of the first is the domain of the second, right? So, well, let's make that clear. That's what makes it possible to do the substitution. Okay, so then what we're saying then, the composition denoted by G circle F of F and G, what is it? Is a function. So G circle F from X to Z, so as just we saw it, skipping the intermediate step Y and going straight to Z, okay? And given by that equation that we just saw. So G circle F of X is equal to G of F of X. So that is the definition. As you can see once again, sets, functions, elements of sets, that's it. There's nothing else. So everything from calculus is left by the side. Okay, so that is the combining. I especially like that example of combining a parametric curve with a function of two variables, trip with terrain, elevation. It's all good, but we have to go with more abstract things. So one example that I want to explore a little bit that just occurred recently to me, one example of functions that also can be used to study things, but outside of mathematics. The function I want to talk about is from, which way? Okay, you'll tell me which way. There are two sets. One set is the Senate, and the other one is the states. So imagine here I have a list of states, and on the left I have a list of senators. So maybe it's better if I senators. Better. Okay, so that's one set and that's the other set. Okay, do you see a function here?
There's senators for each state.
Yes. Yes.
Is it two?
Two, yes. Very good. Which way did the function go? From senators to the state. That's right. Why not the other way?
States to the Senate doesn't make sense.
A person represents, you have a state, you have a senator represent.
Numbers of senators?
What?
Is it numbers of senators or just like names?
Name, so lists. Both of them are lists. So one is has 100 elements, and so these are sets, 100 elements, and this one has 50 elements.
Yeah, definitely 50 on that.
So this way, why not the other way around? No, wait a minute. Did I? The other way around.
Yeah.
Okay. Why not the other way? So this is say X and this is Y.
I honestly don't know why.
No, hold on a second. Senator? Yeah, okay. Not the way around because
Like for every X there is a Y, but for Y there's more than one X.
that's right. That's right. It would not be a function because there it would have two outputs.
Oh.
For one input.
Okay, that makes sense.
But this way, one senator represents only one state, but every state represented by two senators. Okay, so that's the problem. Okay, so before we move on to compositions, is it one-to-one onto? One or the other? Which one?
It's on to.
Onto, but not one-to-one. because there are two every time. Okay.
What about like the Virgin Islands?
Yeah, they don't have senators.
Yeah,
And they're not state either, so
but
Let's just live in a
it's
happy
unfair,
world.
I know.
Live this
So,
way.
and I will take a survey while I'm, and we'll make the road trip too, we'll.
Yeah, we go to the elevation and group.
but like 600 wasn't on that
We'll make
graph,
your point.
so that made it not onto.
Right.
The Virgin
Well,
Islands doesn't
okay, so if
say-
you want to make it not onto, add something to states that are where Americans live, but they are not represented by senators such as D.C., Virgin Islands, and some other possible places. Portland. Well, I don't know. So territories. So territories and D.C., if you add them to the list of states, then the map won't be onto, and then you can make a case this way, mathematical case for, writing this wrong.
Yeah, they don't have senators.
Right.
Google got my back.
Okay. Well, I mean, that's not hard to figure out without Google, just doing the numbers.
Oh, yeah,
150.
you're right, 100 of them. Yeah, you're right. What the heck?
So, okay, so let's create a composition with something. So from the states, now I could come up with any kind of function. So any characteristic of a state, for example, population, could be another function. So from every state, list of states and list of populations. Okay, so I could put here once again, it's my choice. I could put here a number of possibilities. I pick the easiest one are the reals. Okay, even though you cannot have fractional populations. Okay, you cannot have 3/3 of a person, like 1/3 of a person living anywhere. So you can make a case in choosing Z instead, or you can limit the population not going too far beyond, say, 300 million, something like that. So it doesn't matter much. Usually you just pick the simplest one, and you can see why it is convenient to take it as large as it is convenient, so that then it is easy to make compositions. Right. So for example, if I made for example, you can see how the drawback of omitting, say, D.C. from that list of states, even though it was totally according to the Constitution, then if we try to from the rest of that the other function figure out the total population of the country, we can't, because we are limited ourselves to states only. And so if there is a piece of that somebody is not, some people are not represented by senators, then they are not counted as a population. So that's a problem. So in a sense, making the codomain as large as possible is probably a good idea. Okay, so population, what else can you think of? I don't know, the area, a population area, the size of the state in a number of ways,
Counties.
number of counties, yeah, anything, yeah, anything non-numerical. Can you think of a characteristic of a state that is not numerical?
Like, like they have like their state, like their, like state animals, state flowers.
Okay, that's fine. So animals.
It's not
Yeah,
numerical.
animals.
You take the set of animals, and then there is a correspondence from state to an animal, but is it one-to-one and onto? First of all, it's definitely not onto, right? What about one-to-one?
There's one.
I think it's one's one, because I don't think they don't have the same animals for every state. It's called a state animal for a reason,
Right.
you know?
What about the cardinal?
The what?
The cardinal, the bird.
Is it used in other states too?
I lived in Illinois, and they have, yeah. I discovered, I was so surprised that when somebody told me West Virginia has cardinal as a state bird or animal.
State bird, but their state animal could be.
Well, close enough. Yeah, maybe it's different.
Yeah.
They have it on the license plate. Red bird on the license plate of Illinois.
Yeah, so, but we have like a.
They're haters, all right?
So in other words, it might be, I cannot vouch for it, but it doesn't seem to be on one-to-one. Okay. Another way to create non-numerical outputs, just combine numbers together into vectors. So for example, I could take population and area and create a vector of two numbers. So you can collect all kind of information, all characteristic of states that they can think of, put them in a vector, and that will be your output. And then all of a sudden you have like a function from states to, I don't know, 100-dimensional space. Okay, so, well, just an idea. Okay, so that is a composition, and then that is from the states to these characteristics, especially from population would be then if you compose it, then every person on the list of senators will have a corresponding population of the state that he or she represents. Okay, so that will be the composition. Or animals. So then, I don't know, if they wear a button of the state bird on the suit, then that would be a function from senators to birds or animals. Okay, so all kinds of functions might appear. Okay, so
What's Illinois state bird?
what?
So what's Illinois state bird if their state animal is a bird?
I assume that it was the cardinal.
Hold on.
I assume. You can certainly look it up,
It's a
but
cardinal, and so is ours. We share that, so that makes
Yeah.
it
yeah, it is.
onto.
It is strange. Yeah.
Really? Maybe it's a different type of cardinal.
Well, maybe it is. No, it looks exactly the same.
Cardinal.
And
There
ours
you
is a
go.
northern cardinal too.
So
That's
that's,
depressing.
so that means that we're onto it then, right?
Okay, let's go back to one-to-one onto. So under what circumstances we have both and why we care, that came up last time. So f from x to y is one-to-one and onto. Then is called a bijection. So surjection, injection, and bijection. Okay, so you don't have to use those words. So once again, one-to-one is fine, onto is fine, and one-to-one onto is also fine. So I'm fine with that entirely. So remember why we care about bijections. It came up because they all have inverses. So then we're going to talk about that next time.